Good afternoon, everyone, and welcome to our live ATS webinar. Today's all about VoltServer, intelligent power and data infrastructure for smart building architects. I'm Fulgence Henry. I'm your moderator for today. I'm also accompanied by our ATS team who will support us throughout the event. Today's seminar features one AIA HSW, one AIBC core learning unit, and one AAA structured learning unit. We will report AIA, GBCI, and AIBC credits on your behalf within 10 business days. If you're a member of AIA, GBCI, AIBC, please check to make sure that your association numbers in your ATS account are accurate so we can ensure a smooth crediting process. And for everything else, you'll get a certificate in PDF form. That is one certificate for every course you take with us today, and those will be available immediately after entering your session code. And if you're new to the session code process, I'll review that after the session is over. And at the end of today's course, I'll provide you with a session code that you'll enter into your ATS account at atsseminar.com. This number will confirm your attendance and guarantee that the credit you earn today will be recorded. Now, let's go over a few quick housekeeping notes to help you get the most out of today's session. Use the Q&A panel for all questions, including session codes and anything you'd like our speakers to address. Please do not submit questions in the chat. They may be missed, and we won't be monitoring that space for Q&A. Also, we kindly ask that you do not post questions anonymously. We are unable to verify your attendance for credit purposes when questions in the Q&A panel come without a name attached, so make sure not to post anonymously. An important note for Zoom attendees: if you're joining via mobile browser, certain features like the Q&A may not be functioning properly. For the best experience, we recommend using the Zoom app. And they are there. If there are handouts for the course, they're located on your ATS account dashboard. The presentation is available in PDF format also at your ATS account dashboard. If you have any issues with downloading that, please let me know in the chat and I'll make it available for you. Also, if you're watching in a group or conference room, please make sure that each and every one of you are signed into the event using your individual Zoom webinar link that was sent to your email. That link is attached to your ATS account, which is how we report credits to the correct person. So if you're not logged in with your unique Zoom webinar link, please take the time to do that now. And if you're having any technical difficulties, please try logging out and then back in. We find that solves 99% of the issues. However, if you have an issue after that, please let me know in the Q&A panel and I will do my best to help you there. And with that, please help me welcome Jeff and Matt here to present intelligent power and data infrastructure for smart building architects. Gentlemen, hello.
Good afternoon. How are you doing today?
Good, great. How are you?
Good, real good.
Awesome. So welcome. And whenever you're ready, please feel free to go ahead and share your screen so you get your PowerPoint set up there.
All right.
All right, we are all good to go.
All right. Cool. Thank you. Thank you, everybody, for letting us share about intelligent power and data infrastructure for smart building. Myself, I am Jeff Krauns. I am a director of technology at VoltServer, and Matt Conger is also joining me from Sinclair Digital Services to talk about some of the application stuff. Just to jump into the presentation here, you pretty much covered this, I believe. It's all about the credits. There's the course information. This information, any related information or detail you want, by all means, reach out to Matt and myself. We are always here to answer questions. The material is protected under copyright law, so please, if you're going to download it and share it, just please get our approval first, just because there's a lot of information here that's specific to the architecture, but also specific to deployments themselves. So, course description. What we're going to talk about today is as smart building technologies evolve, so must infrastructures to support them. This course, we're going to introduce architects and design professionals into the latest advancements in intelligent power and data delivery. Really what it comes down to is what's the most efficient and best way to provide data and power to remote locations around a building to power things. And we'll talk about what those things are. It very well can be lighting, access points, access control panels, security, video conferencing, all that really cool stuff, even charging stations. So if you think about your desktop, most of the stuff on your desk is actually USB-C. You're using a wall wart to convert it, so why not just power everything straight up DC through USB-C? Learning objectives. So we're going to describe how to build for the future to enable deployment of emerging technologies. And we're seeing that in the market today. Like every time you turn around, there's another technology that wants to be deployed in the building. As I was putting this deck together, I realized, like, I'm going to kind of date myself here, but when I started my career, we did everything on pencil and paper, fax machines. When things like, token ring came out, it was huge. When things like digital pagers came out, it's huge. Now we're looking at gigabit to the desktop, which is pretty cool. Also going to demonstrate how to eliminate the need for intermediate distribution frames or IDF closets in a building using something we're coining as distributed edge technology or distributed edge systems. We're going to understand how to bring fault managed power and communications within the same pathway. That's the cool thing about this architecture is you don't have to have a secondary power distribution for to power the devices. It actually can all be done in the same pathway or in many cases in the same cable, which is pretty cool. We'll explain how to easily back up all critical infrastructures. In today's day and age, security cameras, access points, data communications are critical infrastructure. Instead of having UPSs all around a facility, everything can be centralized and you can distribute that UPS around a building or campus to back up all that equipment. We'll learn how architects how one architecture can be used for security, access control, Wi-Fi, lighting, video conferencing, charging stations. But I want to note there, and so much more. There is so much that this technology can do. We're just going to focus on a few aspects, but it's a very cool emerging technology. So I want to jump into a little bit about the history or where we are in the world. Smart connections are growing every day. The number of security cameras that are going into campuses. And when I drive around, I pull into a university just to look at the number of cameras that are actually pointed at me by the time I drive through the gate to the time I get to my conference room. It's just amazing how much security there is out there today. So smart connections are growing, but it's not just for security. It's also access points, communications, safety for blue light poles. And with the advent of things like AI, there's just so much more that's going to be out there. Now, the question is, you have all this equipment that is out there that now needs power. How do you do that safely and protect the people from shock or from power issues? So that's really the safety of fault managed power, because it actually is managing faults. So you're actually able to get touch safe power, even though it's thousands of watts of power. And then the other thing, as you're pushing all this technology out there, is how do you manage it? There is so much that can be done that you're used to seeing in the IT world, which is for management, but power typically has been kind of a flat, dumb network. Well, now you can actually manage it in IT-like infrastructure. And I'll kind of explain what that means as we go through the deck here. So fault managed power is solving all those problems of distributing power to remote locations around a campus, building, hospital, school, you name it, with a significant reduction in installation cost. And really that comes down to quicker to deploy, easier to deploy, one pathway. And we'll kind of show what that looks like. Also lowering operating expenses, which really comes down to both on the installation side for deployment, but also on the manageability and usability down the road. It adds a lot of features and functionalities. Fault Managed Power adds a lot of features and functionality to be able to remotely manage and determine power levels at the remote endpoint, switch, device, whatever it might be. And then also improved efficiencies. We're doing everything, or Fault Managed Power is doing everything typically DC. So there's a lot of efficiencies that can be gained. But the big thing is reduction in mine materials. It is, thousands of watts of power off of skinny gauge conductors. So you're talking cables the size of, Cat5 or a little bit bigger, but also thousands of feet away, which is pretty cool. So fault managed power is really transformative. It is a new way of providing power, and it is now under in the latest NEC code book, it's under class 4 power. That's really what fault managed power is. And at the end of the day, what it's doing is taking energy in from a centralized source, where the electricity comes into the building. It then takes that energy and it could be AC mains, it could be a DC power plant, could be UPS, could be renewable energies, whatever it might be. Takes that into a transmitter shelf and then distributes it around the building. At the place where the device is being powered, there's a receiver that converts it back into conventional power to then plug that device in. And in the upcoming slides, I'll kind of dig through what that looks like. Give you a little bit better understanding of what fault managed power really is. So I like to use this example, and in this case, I'm saying it's a pole out in the parking lot, pole on a campus, but it doesn't have to be a pole. It could be a remote location inside of a building, could be a remote location inside of another building. So the challenge is all this new architecture that's being installed requires a lot of bandwidth. So you have to pull fiber out to it, especially high definition cameras, for surveillance, whether it's public safety, 4G, 5G, you name it, lots of bandwidth. The issue always is you got to get fiber out there. Now, where do you plug the thing in? That's the challenge. Yes, you can run AC out there, but that gets costly, and that actually sidelines a lot of projects because of that cost to deploy. If you're going to go long distances, you probably need submetering, or if it's outdoor, buried conduit specific for that power. If it's real long, you may have to have transformers in place to push that energy at those long distances. All that's additional cost. Still need a pathway for the fiber. So you still have to, there's a conduit for the copper, the power, and also a conduit or a interduct for the fiber. If you want to have backup, now you have UPSs or battery in the zone box and at the head end. Once again, that adds additional costs. And then that zone box, that remote location may not be environmentally controlled. And if that's the case, batteries don't last long. So that's the challenge, right? Fault managed power really solves that delivery challenge. And at the end of the day, now it's one pathway, fiber and copper run in the same conduit or same interduct, or could be hybrid cable. Now, all of that stuff at that remote end, all those sensors, lightings, Wi-Fi access point, you name it, is all now backed up to the core distribution, core UPS. So it makes it much easier to deploy, quicker to deploy. So digging a little bit deeper in about, fault managed power and, kind of how it works. Like I mentioned earlier, you're taking conventional energy in, whatever that source might be. If you look at some of the net zero buildings, it is, they're using solar, they're using wind, they're using PV, they're using a whole bunch of different things to bring in energy into a collection point, but then getting that collection of energy out to the remote sites is the challenge, right? And that's where fault managed power comes in. It's basically taking that energy into a transmitter shelf of some sort, a device that provides the fault managed power, and then it pushes that power out to the remote location, up to 6,000 feet away. And it can run on, 18 all the way up to 12 gauge UL 1400-2 cable. So what it's doing in between that transmitter and receiver is it's actually pulsing DC, so packetized DC. So it's like 1.5 milliseconds of energy, and then half a millisecond of a validation. That validation is saying, hey, does anybody have their fingers across it? Are there any faults? Are there any issues? If there are, it stops the flow of energy, which is pretty cool. It's kind of like, a circuit breaker, but to the point where it's safe to the touch. So really, really cool technology. It samples that every, like I said, 2 milliseconds, so 500 times a second. It's looking for impairments. What that means is there isn't going to be a fault where the cable's flopping around because it's arcing. It's actually going to shut down and remove the power source. Once that fault clears, it'll start the flow of energy back up again. But like I said, at the end, it doesn't necessarily have to be powering a switch. It could be powering something else, some other device. It may be carrier radio. It could be USB-C charging stations, lighting controllers, you name it. It doesn't really matter. It's just, in this case, I'm showing a switch. So I mentioned earlier about information technology like management for power networks. So this is the other cool thing. AC or traditional power has really been kind of a flat thumb network for so long, and this is actually adding usability that IT infrastructure or building maintenance people love to see. It takes it down to the granularity where you're looking at power levels to each remote cabinet. One thing I want to mention is that head end, that point to point that I was showing you here. It actually isn't a point to point. It's point to many point. So this transmitter shelf can go out to multiple different remote locations. So it's not a specific point to point. So the other cool things about this management-like network is now it means that a NOC center who's managing it actually can reboot things remotely. So if there is a box somewhere in a building, that facility could be on the other side of the country. If you have access to get into it, you actually can reboot that device. Not saying a reboot is the fix for everything, but man, if you have access to do it, it's pretty cool. It shows power levels of every endpoint, so you can manage, you can determine whether or not things are plugged in. But there's also a lot of cool things you can do on the usability side of things, which is policy control. So maybe you want to critical power prioritization. Let's say a building's conventional energy, the power coming in from the power company is out, right? And it's running on batteries. Well, you can actually choose which endpoints you want to keep up during that power outage event to maintain that battery plant longer. It may be the critical stuff. The security cameras might be, the door access systems might be top of the list. Well, maintain those and shut down the stuff that you don't care as much about during that outage. At the end of the outage, when the power comes back on, all that stuff is brought back up. Pretty cool. So I'll talk through some of the applications for fault managed power. Now, granted, these are just some applications. It's not everything. So these are the ones that we're seeing right now as typically deployed. So if you look at campus environments, large campuses, universities, business campuses, private wireless, it is carrier cellular wireless, cameras, sensors, signage, blue light poles for security. That's a big one. Call boxes and lighting. That's in the campus stuff. Parking garage, it's the same thing. I mean, last time you pulled into a parking garage at the airport, there's probably little pendants hanging down from the ceiling telling you whether or not that parking spot is available. All that stuff needs power. All that stuff needs network. So in parking lots, it's a lot of cameras, sensors, signage, lighting. Now, a lot of the lighting that we're looking at is, PoE-based lighting, and Matt will talk a little bit about that later. Warehouses, it's the same thing. A lot of automation going on in warehouses. Private wireless is a big deal. When you have automation, you want to do asset tracking. That's pretty cool. But cameras, also sensors, call boxes, everything else. Offices, it's the same thing, same stuff, but you add a few other things. Now you can do USB-C to the desktop. Pretty cool. Hotels, getting into even more. Some of the hotels, things like mini blinds, things like mini fridges, lighting in the hotel, especially a lot of the back office or back hall lighting. Security, obviously a big thing. K through 12, same thing, wireless camera sensors, vape sensors, USB-C charging. I mean, it's amazing the amount of you're talking gigabit to the classroom now. Whereas, when I was in school, we were lucky if we had dial-up. Secure facilities, same thing, fence lines, camera security, big thing, guard huts, lighting, but we could also, fault managed power can also be used for things like BMS panels. So now all of those BMS panels within a building can then, for door entry systems and automation, can all be backed up to a centralized spot instead of batteries in a cabinet. So that's just a sample. There is so much more that can be done. Like I said, this Class 4 was ratified into the NEC 2023 code book. So it's out there, but fault managed power has actually been around for a long time. Matt, you want to hop in?
Yeah, sure. Jeff, I think some of the things you want to stress more is with the advent of fault managed power and being able to pull data or fiber cabling or even Ethernet cabling along the same pathway, you're also eliminating all that MC or conduit, right? So because it is treated like class 2 wiring methodologies, there's a huge sustainability benefit that comes along with fault managed power. There is no greener building than a building built with fault managed power. Do you agree with that, Jeff? Jeff, you're muted, by the way.
Yeah, I had to find the unmute button. I apologize. Yes, I do agree.
So let's go. So now we're going to move into, Jeff talked a lot about the technology, which is fault managed power, and the benefits. And so now we're going to talk about how we combine FMP with other technologies to deliver holistic solutions. Because at the end of the day, it's understanding or being able to visualize how can I apply it to add value, add resiliency, save money, be more sustainable, whatever that benefit is that you're trying to achieve. We're going to talk a little bit about some of those use cases. And so this is also a good time to ask us questions or to interact with us as we're going through this. So if you think about our buildings, the technology is super valid. So Jeff touched on some of those things about how we have 1 gig going to an AP. And the idea is that, hey, as we move towards whether you're a school where every child has a device or us in the work environment, we're surrounded by computers and processors, and the need for data. Data is of great value and it helps us to make decisions in our lives. But in order to deliver that data, we've got to have a resilient, fast, and power-rich network. And so you or your clients have to balance, it's expensive in times to deploy these things, but yet we need those complexities. So how do we do this in a cost-effective and resilient manner with these challenges? And so the buildings have to be able to adapt. They have to be agile. Building occupants are moving around continuously. They need high-speed internet, whether it's metaverse activities or just using their BIM tools to design with, that data and being online and the being able to have these Zoom meetings and have it reliably are just absolutely critical to what we do today. And if you think about that's just today, but where will we be in 5 or 10 years as we move to more edge processing and edge intelligence of in devices? Those things become even more power hungry and even more data rich. And this, even when if they're mobile devices, those things need really resilient, fast access to the internet, to where there's, it's less than even 1 millisecond of latency as those objects are moving around. And so we've got to be thinking about how do we make these buildings good for today, but then also over the 50-year life of these assets, how do we protect those values and how do we support the changing needs, right? So the building's got to be agile.
Yep. So interestingly enough, I kind of have a real world example. My daughter actually just started medical school. She's in her first year, and first year med school, everything they do in anatomy is all done through VR, which is pretty cool. But it was an interesting thing. Like, it was the first time I got to put on a VR mask and actually look at, the anatomy of a person. It was pretty cool.
And so the key challenge to think about are that more endpoints and more devices means more power. As you add more devices, you're going to need to either add more cables or upgrade the quality of those cables to continue to increase the power and bandwidth of those spaces. And so we can't have lower network performance. The copper is got to offer more bandwidth, or we got to find ways to do that. And so as you add more cables, it gets bulky. You end up with cross-talk interference with your electrical systems. You end up with heat rise, all challenges related to the networks of today. And another one is higher costs. So endpoints require long runs, and the cost to add these cables can be significant. So think about going through and literally there's still buildings out there that have Cat 5e and they're going to 6 and 6A. Imagine outsourcing that task to a third-party contractor, shutting down your operations to pull new cabling, and then the one day, no, you got to do it again. So those are things that people are thinking about. When you are doing that and you need more network gear and it lives in these things called IDF rooms or closets, those spaces are super expensive to build. And when I say build, you have to run electrical to them, which is conduit and copper and breakers and transformers. You've got to air condition those space. Then you might have to provide physical security as well as cyber security. And then they take up valuable real estate. At the end of the day, buildings are not inexpensive. They've only gone up in price significantly since COVID. And I don't see it stopping anytime soon, especially as we continue to see copper prices rise globally. And energy costs are only going to go up. So we've got to find ways to combat that. And then lastly is the designs we do today, they've got to evolve to utilize these new technologies. And so the design community will catch up and start to deliver this and add value to our end users. So let's take a look at a traditional building network today. So I don't come from an IT background. I come from building controls. And so, but if you're an architect or an MEP, or you might know that there's a main distribution facility or an MDF. And so that's usually where your core switches live. That's where so you'll have data, and usually your internet service provider is running fiber into that space, and that's where your data is going to spoke out from there. So because of distance and power limitations with power over Ethernet or category cabling, you don't want to exceed 100 meters from from a network switch to an endpoint or to a power device. And so because of that, you end up with these things called intermediate distribution facilities. And they're scattered around a facility or on floors of a building. So you run your data from your MDF to your IDFs. Then once you get to your IDFs, you're then running power and data out to your endpoints. An endpoint could be a camera, an access point, a TV that needs data, a data jack, a phone. And so these physical spaces cost a lot of money to build and maintain and support in today's network. And so our firm, and working with Fault Managed Power, or this new architecture has been created to combat the challenges of these traditional networks. From that, I kind of skipped a step, but this one goes along with it. From the IDF rooms, this is showing what a typical corridor might look like going to an endpoint. So the red lines represent Category 6 or Category 6A cabling from the IDF to an endpoint, such as the phone or the access point or a clock, even audio visual. And those numbers of points are growing and growing and growing. And so we're ending up with really long cable runs, average about 200 feet, as well as with significant cable bundles with heat issues. It gets to a point where if you go into an existing building, a building that's like 12 years old, you look above the ceiling, or it does have a ceiling tile environment, look up in that ceiling plane and you will see spaghettis of wire. It can get pretty messy at times.
Yep. And I was recently at a hospital talking with a customer at a hospital, and the challenges they have running cabling like this down a hallway or down a corridor with infectious disease control regulations is huge. So, they have to cordon things off in order to break open the ceiling tile to run a new cable. That is a challenge and difficult, and definitely impacts the operations in the hospital. But the same thing goes for an office building. Like, you don't want to interrupt work to pull a new cable. And if you're pulling, hundreds of feet of cable, it definitely can interrupt work.
Yeah, so the question on that is, how do we provide more power and more data at one time, or at least power and data infrastructure, or pipes, I'll call them, to be able to support that without interrupting the what's going on below where people are moving around. And the great lead in here is that, well, when you do go make those changes, it's terribly disruptive. In a school environment, a lot of times they'll do it on the weekends, or they'll wait till summer, and they'll do it over holidays. Same thing goes for commercial world, warehousing. You've got to find ways to get this work done. And if you got to do it during the day in a 24/7 or during off business hours, like a hospital, it can cost millions of dollars in lost revenue, as well as millions of dollars in actually doing the work. So we've got to find ways to I guess lessen that as technology changes from where we are today over the life of our building. Just think about, like, when Jeff said we didn't have super fast networks growing up, or a lot of us, versus today, we need more and more and more, and it's just going to continue to change. So what's the solution? The solution is this thing Jeff mentioned earlier called a distributed edge architecture, is what we've coined it. And a distributed edge architecture exists purely because of fault managed power. Without fault managed power, a distributed architecture doesn't make financial sense, or it doesn't make sense for delivering greater value in the built world. But with FMP, combined with things like Power over Ethernet, USB, low voltage DC, low voltage cabling infrastructure, fiber cabling, all those things together with DC power is what's creating the benefit. So it took FMP and all these other technologies to come together to create value in the built world.
Yep. So really what it is it fault managed power enables the equipment to be where the equipment is needed and doesn't force the equipment to be placed in a closet because that's where there's access to power. That's the whole premise, the whole concept behind fault managed power. Bulk power to where it's needed versus put the equipment in a location because that's where the power is.
So here's a graphic of what a edge architecture looks like. We're gonna have a couple different graphics as we move forward. So if you don't follow on with this one, maybe the next one will get you. But it's a hub and spoke architecture. So I like to talk about. We'll use the MDF room as the example. So we'll play the way the solution is. You'll typically have some sort of the enclosure that lives in the MDF room, and that enclosure is fed either AC or DC power. When I think of a commercial building, a large commercial building, you have 40 in the US, you have 480 volt, three-phase power coming in, and then inside of this head in are things like your core switches, your servers, but also the fault managed power distribution. So earlier, Jeff said, hey, you have these things called transmitters, and the transmitter is what is converting that power coming into that enclosure, and then it is outputting FMP from there. And all that lives within this head-in assembly. Then from the head-in assembly, it's going to spoke out. And when I say spoke out, it goes to these things called edge IDFs. The edge IDFs do not live in a traditional, well, you could still build IDF rooms if you want them, but you actually, with this concept or this solution of the edge architecture, it's to move the network switches in the edge processing closer to the endpoints. And the way you move them closer to the endpoints is you mount an edge IDF on the wall or in the ceiling plane. Well, those edge IDFs that might have like be able to do power and control lighting, power and control shades, power and control or power and communicate with access points, they need power and data. And so the cabling or the pathway from the MDF to each of these edge IDFs is a hybrid cable made up of DC, of copper and fiber. So we're moving the power over the copper and the data over the fiber. From the edge IDF, you spoke out yet again to your endpoints. So an endpoint can be anything like Jeff was talking about. So if you have you want to power a low voltage VAV damper, yep. If you want to power and communicate with an IoT sensor or an access point or a phone or a camera or a light or a computer or a raised lower desk or a USB outlet, all of those things can be supported. And so what you'll see is buildings continue to evolve and technology continues to evolve. More and more endpoints will be DC powered or even AC powered. With fault managed power, you can convert back to AC, but the more DC powered endpoints, the better and the more cost effective it is. And not just cost effective, but it uses less energy. The equipment lives longer. It has less heat is created at those endpoints. There's huge benefits just to using direct current power throughout the architecture. And if you want to, sorry, Jeff, we'll go back one time. Right. Also back, there's those on-premise servers that live in that head-in assembly. You know, that is what is controlling and communicating with all those different systems. So whether it's access control, whether it's cameras, whether it's lighting, whether it's your IT network, that's where your servers are all live. And then that's where we're going to do all of our air gap and as well as other cybersecurity means of protecting the system from there. You got the next one now, sorry. So what are the technologies that make up an edge architecture? The biggest one, the most beneficial one, the reason this all exists today is fault managed power. So safe, high wattage, digital power distribution. to deliver DC power over super, super long distances, but is treated like Class 2 low voltage wiring methodologies. No conduit, run in the same pathway as data. Power over Ethernet. If you've not heard of Power over Ethernet, it's how we move power and data over category cables. I describe them as little blue cables that you see around. They're not always blue, but that's the idea. So it's a standardized IEEE compliant solution for moving power and data as a Class 2 method, a wiring methodology. XPoE. XPoE is a complementary to Power over Ethernet with a focus on lighting. PoE by itself is also for lighting. I always forget to say this. Power over Ethernet is used for so many different things, whether it's lights or desks or computers or phones or access points, or there's tons of objects out there that work with PoE. There's other objects or other solutions like XPoE that allows you to drive luminaires without having additional PoE components. So if it's a great complement to the solution. And then the last one is low voltage direct current power. So that's DC power that's below 60 volts, below 100 watts, also treated like Class 2, and to use to just provide power to objects. So these other, the other technologies, or PoE is great for power and data versus just LVDC is just I call it dumb power. It's sure someone would have a better technical term than that, but it's just for moving power to endpoints.
Yep. So all those things on the right, low voltage DC, PoE, XPoE are all distance limited, and fault managed power helps enable the adoption of those technologies because it pushes bulk power out to where it's needed, and then PoE from there to the endpoint. It helps drive the solution, the architecture.
Same look of the building we looked at either, and now you see all these blue dots scattered around the space. So these are edge IDFs. So you went from 6 centralized, physically built rooms to a number of edge IDFs that are closer to the endpoints. And so when you do this, we have 1 MDF, 0 physical walk-in IDF rooms. We've eliminated all the square footage associated with those rooms and the cost of those rooms. We still have our MDF and we still have our MDF square footage, but we've reduced reduced cost to build that building, or we've given space back to the people that are using the space. Like, we build buildings for people. Well, now we build data centers for robots, but that's all evolving. But either way, we want to give as much physical space for the reason it's there, not because for systems that we don't look at every day, right? If there's ways to still have those systems and do it better, but not use physical space, that's definitely a win for architects. Then we're a zoom in of the corridor. So here there is 1 edge IDF supporting roughly 2 areas in this example. There are different sizes of edge IDFs to support different sizes of spaces. And depending on the number of endpoints will determine where you position your edge IDFs. It's really up to the designer to say what is appropriate for this facility or this space. Now your distance runs from those edge IDFs. It's a 30-foot patch cable. So no more building jacks for 200-foot runs all day long. It's literally, hey, I need to add a new IoT sensor. Great. Here's a 30-foot patch cable. Here's the sensor. Go throw that cable across the ceiling, mount that sensor and plug it in, and you're done. The yellow line here, that does represent the hybrid cable, but it includes the fiber to the edge. And so fiber to the edge is how we're increasing those bandwidths. And we're going to be able to provide, I've seen it to where these are providing 10 gigabit of throughput or at least it depends on the networking gear that you have, but you could have upwards of, I think 60 gigabits of throughput very easily with this architecture. And so the network performance is much greater. So who all went? I like to call the edge architecture as a triple win. The person building the building wins because it's easier and faster. The person paying for the building wins because it's more cost effective, and the people in the building win because we can provide better edge architectures can provide a better experience for those occupants in the space, whether it's kids learning or people working or administrators administrating, whatever that is. So the system's going to provide more equitable access to data and to the internet. So it's literally it's leveling the playing field so that everybody in the facilities are getting ultra fast internet wherever you are in that space.
Yeah.
With the faster internet. Sorry, go ahead, Jeff.
And that could be, owner occupied, but that also could be like a real estate developer who's trying to entice tenants to come in. The more technology they have, the more apt they are to fill their space as a development or a building owner.
Great. We can streamline operations. So because there's less cabling and because the network lives longer and more objects are connected, systems like this can be supported remotely, right? Because it's all software defined networks. And then because it's less materials and lives longer, less people can support more stuff. And so we're reducing those IT costs, but it's significant in the materials department. Simplifies the maintenance. I always forget this one, Jeff. When you go to a hub and spoke architecture using FMP, and we're going to show you examples of this in a second, is that in a traditional IDF scenario, you put UPSs in all those IDFs. And then the IT staff has to remember that they've got a failing or a UPS that's nearing end of life, or maybe it's acting up and they have to service all those. Well, now with a hub and spoke architecture, you have one large UPS that's backing up the entirety of your system. So it's much easier to service and manage and provide greater resiliency for the life of your building. Less material, we touched on that. So 100% less conduit, 60 to 70% less copper. Those are huge benefits. Energy and space. So less energy. Like if you were to compare an edge architecture for lighting as compared to a traditional lighting network, an edge architecture is going to allow you to achieve 30% more energy savings as compared to the exact same system done with line voltage. There's multiple tricks to get to that 30% greater, but it is absolutely that much better. So I could take a line voltage lighting system with motion sensors and daylight sensors. I could take an edge architectural lighting system and show you how to achieve 30% additional energy savings on top of that. And those energy savings, they don't just apply to lighting. It's the elimination of AC to DC power conversion. Just by eliminating AC to DC at all those endpoints, the endpoints live longer and they use 5 to 20% less energy, depending on what the endpoint type is. Then because we're not building those IDFs, you're saving on power, you're saving on space, and you're saving on cooling. Last one is, and it's probably, to me, it's one of the coolest one, but a lot of people don't seem to think about it, is safety and security. It is low voltage, so you're significantly reducing the risk of fire and shock. So there's the benefits to us people, but then there's also to your pocketbook. So can I get lower insurance rates because I've eliminated shock and fire risk, or greatly reduce those things? So summarization of benefits to an edge architecture: save on square footage, eliminate IDF rooms, using safe DC power, convergence of IT and OT systems. We'll show you examples, super scalable, really fast, ultra fast network speeds, doesn't require specialized labor, energy savings, and less materials. This is a photo or an image of what the cable that looks like that goes from the head in out to the edge IDFs. It's a hybrid cable, so it's multiple pairs of copper with multiple pieces of single mode fiber that are put together in one jacket, and that allows that to be pulled at once as well as provide lots of data and power at the edge. A lot of the implementations we've seen of edge architecture, the clients are opting to provide a couple extra pairs of copper and some extra fibers, and they're referring to that as dark fiber and dormant copper. So if you ever did want to add even more bandwidth or even more power, the necessary cabling infrastructure is already there day one. Just grab the extra pairs and grab the extra fibers, and you're moving. So who's doing it, and what are some real world examples? Nicholas County Schools in West Virginia utilizes this at their schools. For the photo in the left is a image of an edge IDF. So it's it's actually all three of these images, sorry. First one is with the door closed, looking at it from below. The second one is with the door open, so you're looking at it from the hallway. And then the third one is also, of course, open. Well, the things I like to point out here is it's supported from the deck. It does have pneumatic arms to make it easier to open. It's super easy to open and close. And then do you see how, like, because it's at the edge and there's more of these distributed enclosures around, do you see how close it is to an endpoint? Like if you just look in the photo in the middle, there's a sensor visible, there's a light, there's a TV, there's probably a data jack on the wall that I can barely see. But can you visualize how short those Ethernet runs are to those endpoints? And then if you look on the right, so the yellow cables, that's your fiber bus. So that's how we're moving the fiber to these edge hardened, convection cooled, fanless network switches that are designed to live in this environment at a very robust means. So there's your fiber and your data. And then the red and black or white and black wires, that's the fault managed power entering, being received from the transmitter and then received. And then the receiver is then converting it to whatever the power that those endpoints, those end switches like. So in this example, these edge hardened switches like a 57 volts DC power. And so there you go, power and data brought together at the edge, converted to PoE, you're in business.
Yep. And then if you want to bring in other technologies like lighting, there can be a lighting controller. If you want to bring in other technologies, it's flexibility is important in this market, right? Having the ability to bulk power to a remote location and then bring in whatever technology needs to be powered at that spot. Lots of flexibility.
Hey, Jeff, I go back to that last one, and I'll say it real fast. Is that so? At their latest build, this particular school district, the building was already architected, and the bid was already done to build it and construct it. So money has changed hands, and so they went ahead and they built physical IDF rooms or these physical spaces. The client along the way elected to deploy this edge architecture, and they gave back three offices and 2 multi-use storage closets to the school. Like that's a ton of space and usable space and value that you're giving back to people, which is what we want to deliver. Westfield Public Schools in New Jersey, another Northeastern project, and they are using FMP to, I think if Jeff, I remember correctly, is that it's mainly there to streamline the resiliency and streamline the backup power with a centralized UPS source. Is that right?
Correct. So it centralizes the backup power to one location in the building, because what a lot of schools, not only Westfield, but a lot of schools, they find themselves spending so much time maintaining UPSs that instead of doing instead of doing actual IT work. So removed all the UPSs, powering switches in the back of the classroom to bring in a bunch of different technologies, anything that can be plugged into a switch port, whether that's a phone, an AP, a call manager system, a clock, IP-based clock, you name it, anything that can be plugged into those PoE switches.
Here's a couple projects that I'm pretty familiar with. There's a hotel, a Marriott Autograph property in Fort Worth, Texas, called the Sinclair. It was a 1920s construction commercial office that was converted into a luxury Marriott property, and the entirety of the building is powered by one head-in rack or enclosure located in the basement. And so it's moving power along with data up to most of the building systems. And I say most of the building systems, your lighting, your PoE refrigerators, your smart mirrors, your phones, your access points, the data jacks, data for the TV, PoE phones, data for computers, on and on and on and on. The only systems that aren't really touched at that property because of it was just early when it was just deployed was convenience outlets and air conditioning. Today, FMP and edge architectures and these endpoints are evolving so fast. You're now able to do all your critical building systems basically if it needs power. Most buildings can now be supported strictly with FMP. Not all of them, so every use case is kind of different. Photo on the right is a world-class distribution facility for Mouser Electronics. It's actually their facility. It's a 400,000 square foot warehouse with 40-foot high ceilings. So if you see the black box, that is your edge IDF. And then from that edge IDF, it is powering, controlling, communicating with all the lighting in this building. There is multiple, if you see the mezzanines in the back in this photo, they're not illuminated. They're now all illuminated. And it's actually mezzanines across this entire facility. So there's thousands upon thousands of power over Ethernet lights utilizing the edge architecture that's only exists because of fault managed power. So fault managed power is changing completely how we power and control buildings. And it makes for a very resilient system. The photo on the part to the right there, that's your head in where the where the transmitter shelves live. You can kind of see a green box in that photo. That is a transmitter shelf with multiple cards of output. And the cards of output in that photo are providing FMP power to these edge IDFs.
Yep. And if you look at the yellow cables up there on the top of the screen, that's basically all the distribution running out to the entire 416,000 square foot facility. Yep.
Awesome. Don't have a photo of this one. It is under construction. It's a Class A corporate office headquarters. It's 270,000 square feet, aiming to be net zero. So it's got a massive solar canopy. It has on-premise battery energy storage systems. This one is doing full IT and OT convergence. So sometimes people use edge architecture for just lighting or just cameras or just data networks. And you can do that, and there's benefits to all those. But the huge money saver is when you converge you collapse or converge your IT and OT backbones. And so what that means is utilizing that hybrid cable to power and power and control more than just one siloed system. So this particular building is doing that. Some of the examples of systems that are being supported by the edge architecture are 100% of the indoor and outdoor lighting for this facility, all the motorized shades, the GPON network or IT network, so that leverages fiber, all cameras, access points, data jacks. I could go on and on. Probably the one that I think is really exciting is this particular company that's using the edge architecture has decided to eliminate all of the 120 volt alternating current convenience outlets in their building and is leveraging the edge architecture to power it. So the system is able to provide 100 watts of USB-C power. And that USB-C power is being used to power the raised lower desks and the laptops and the monitors. I believe there's two monitors on each desk, is my understanding. Eliminating all the IDF rooms and all of its associated HVACs and shrunk the electrical rooms. It's impressive. So this is the evolution of the way we're building buildings. Anything else you want to add, Jeff? Or are we good on this one?
Good. So in summary, safe power changes everything. Fault managed power is significant. It's like, thousands of watts of power can be used in a whole host of applications, as you saw in this deck, and there's a lot more that it can do. Much safer to install since it's all class 2 wiring, no conduits required by code. A reduction in cost over traditional electrical distribution. Fault managed power, it's installs safer and saves a lot of work hours, labor hours installing. We can install very quickly. Fault managed power is more sustainable. It uses less renewable energy because, if you're thinking about it, it's not conduit and large gauge copper. Now it's 18 gauge, 16 gauge cable. So, and then the whole intelligence, adding intelligence to power that wasn't there before. So that's the presentation. That concludes this the presentation. We have a couple slides on the end, but if this is my contact information and Matt's contact information, if you have any questions, by all means, reach out. We are always available to answer questions and can definitely do a much deeper dive. In the end here, I just want to talk a little bit about VoltServer itself, and then Matt will be able to talk a little bit about Sinclair Digital. So coming from VoltServer, we are the pioneering leader for this thing called fault managed power. Honestly, we've been doing it for a decade. So if you've gone through any major airport, if you've gone to any stadium, major sporting event, you've probably used our network. Just didn't realize that we've been powering carrier radios for years. So now we're moving, as fault managed power got codified into the 2023 code book, we're starting to move into a lot of these other applications.
Yeah, and so I'm with Sinclair Digital. We're a Fort Worth-based company focused on, we've created a product or solution, which is the edge architecture that leverages VoltServer's fault managed power or digital electricity. So it's kind of like VoltServer inside or powered by VoltServer. And we've been using FMP with VoltServer since 2016, I think is when we first started playing with it. I was not around then, but our founder, Farouk Islam, was. And just over the years, just perfecting and getting better and getting better. And our firm, we focus on, hey, we want to build buildings using DC power. And because of those benefits we talked about earlier, and then, hey, not only just DC power, but safe low voltage DC power. So we've been on this journey and we've attacked critical systems with our Agile Core edge architecture to power edge connectivity for IT and OT networks. This is just a different view of the topology. You can see all this on our website, just like you can learn more about fault managed power and digital electricity on VoltServer's or Jeff's website. So I'm not going to touch too much on it because we got a slew of questions we got to go over here in a minute, Jeff. The core components is you have your head in that lives in the MDF. Then you have your strand-wise hybrid cable. From your strand-wise cable, you go out to your edge IDFs, and from your edge IDFs to your endpoints. It is that simple. Do you want to jump into questions now, Jeff?
Actually, gentlemen, thank you so much for your presentation. We are over time now, and we're going to have a beautiful Q&A report with all these questions because a lot of great questions came in. So you'll be able to answer all of those offline.
Good deal.
Yes. Thank you so much to you
thank you.
both. We appreciate it. Great presentation. Thank you.
Thank you.
Wonderful. See you guys.
All right, guys. Thank you so much again to Jeff and Matt. That was an amazing presentation. There is the session code for you all, 145752. 145752. Let me go ahead and stop the sharing here. Stop. Perfect. There we go. 145752. And then for those of you who are new to the session code submission process, we're about to get into that right now. Okay, once again, there it is, 145752. And in order to receive your credit for the course today, you'll need to enter this session code to your ATS account. The process consists of the following steps: logging into your ATS account at atsseminar.com, entering the session code 145752, and completing the course survey. So let's break that down. There are two ways you can access your ATS account. The first is via atsseminar.com, and the second is via the ATS mobile app, which you can access using the QR code on the screen right now. And if you go to your account on the website, please open up a separate browser window if you are joining from zoom.us. Right now, we're on the Zoom platform, so go to atsseminar.com. And once there, you'll log in like you did when you registered for today's event. And if you'd like to enter your session codes on the app, please use the QR code on the screen to download the app. And to log in, you'll enter your email address and your password. And if you get to the account, if you get to the website and it says My Account, in the upper right corner, it should be red, My Account. That means you're already logged in. So just click on that and it'll take you to today's agenda. And then on this screen, you'll see the words Enter Session Code next to the course. So you'll see the course there on the agenda, and you'll see that dark blue Enter Session Code button. So click on that. It's pretty straightforward. And then you'll enter 145752 right there in that box and click Submit. So keep in mind, our system closes out the event within 24 to 48 hours. So we recommend entering the code by the end of the day so there's no issues with processing that certificate into your ATS account. And once you've added the session code, click the dark blue circle under the text entry field, and it'll take you to the course survey. And the course survey, you'll have 6 multiple choice questions there and 1 open-ended question for presenter feedback. And you do need to provide feedback in order for that session code to process. So once you're done, hit the Confirm My Presence button. And I'll take you right back to the agenda for the day. And if everything was entered correctly, you should see that green presence confirmed notification. And that's it. And if you have any questions, please be sure to use the Q&A panel, and I'll help you out there. And after you've entered your session code, you'll be able to view and retrieve your certificate. Retrieve by clicking that certificate button and that tiny certificate icon next to the course, and you will see something like this. Here's what your certificate of completion will look like, and it's available for download in PDF format. And again, there's a handout. The copy of the course is available in your ATS account dashboard, and I also shared that in the Zoom chat as well earlier. And if you need any last minute credits, please visit the ATS on-demand course catalog. And please be sure to follow ATS on LinkedIn. Very soon, we have a live video podcast coming up the first Friday of September, and you'll receive more details for that. And thank you for joining us. I'll hang around for any questions that you may have. And please submit the rest of your questions for Jeff and Matt in the Q&A panel. And please make sure that you are not posting as an anonymous, because we won't be able to include your question in the report for Jeff and Matt. Okay, so that's very, very important. Thank you for joining us. Enjoy your day, and we hope to see you back for another webcast soon. Have a good day, everyone.